Now that we've looked at the formation and main sequence stages of a star's life, it's time to move on to what happens after this. The main sequence is by far the longest part of the star's lifetime, so these later stages last a much shorter period of time. As a result, the types of stars produced after the main sequence are much rarer than main sequence stars in our galaxy. However, as we've seen in the lecture on stars, these giant and supergiant stars are also some of the brightest stars around us, so they make up a large fraction of the stars we see in the night sky, even though there aren't many of them compared to main sequence stars. The most important thing that determines what happens to a star after the main sequence is the star's mass. So we're going to use mass to frame our discussion of the late stages of a star's life. In this lecture, we'll focus on low-mass stars. In other words, stars like the Sun. Later on, we'll see how the story changes for higher-mass stars. First, though, we need to look again at the physical forces acting on a star's interior. So we'll return to our discussion of the balance of forces in a star and see how this balance changes at the end of the main sequence when a star runs out of hydrogen fuel in its core.
The end of the main sequence comes when there's no more hydrogen to fuse in the core. Let's return to the balance between pressure and gravity. With no more fusion in the core, it starts to lose the main source of its internal pressure. As a result, gravity causes it to start contracting in on itself. As the core contracts, it gets even hotter. Since it's hotter, more energy is being emitted out to the rest of the star, so the total luminosity goes up, not down. It sounds surprising, but running out of hydrogen fuel makes the core hotter and the star brighter, not fainter. That's because gravitational contraction is a very effective way of generating heat. It just can't last as long as fusion.
Since there's more energy coming from the core, the pressure goes up in the rest of the star. This increase in pressure makes the outer layers of the star expand, so it starts to swell up to form first a subgiant and then a red giant, a large, luminous star with a cool surface and a very hot core. Have a look at the picture on the top right. It shows a comparison between a star like the Sun and a red giant with the same mass. This is what the Sun will turn into when it runs out of fuel in a little over 5 billion years.
This is a common theme we'll see throughout our discussion of post-main sequence stars. When gravity makes the core contract and heat up, the outer layers swell up and get cooler. When fusion support makes the core expand, the outer layers shrink. The outer visible surface of the star does the opposite of what the inner core is doing. This is simply because of the constant struggle between gravity and pressure.
As the core of the star contracts, it heats up. But that also heats up the gas immediately outside of the core. This causes a shell of hydrogen outside the core to get hot enough to start going through fusion. Part of a red giant star's extra luminosity comes from this additional fusion source. So a red giant star has a contracting core of helium, a shell of hydrogen that's fusing into helium, and an expanding outer envelope that's swelling up to 100 times the size of the original main sequence star.
The contracting core keeps heating up until it reaches a temperature of 100 million Kelvin. When it gets this hot, a new kind of fusion can begin, known as helium fusion. The helium fusion reaction is called the triple alpha process. The triple alpha process is much simpler than the proton-proton chain we saw when we looked at fusion in the Sun. It takes 3 helium nuclei and smashes them together to produce 1 carbon nucleus, with a little extra energy emitted in the form of a photon. This begins the process of turning the core from helium into carbon.
Once carbon forms, it's also possible for some of the carbon to absorb 1 more helium nucleus and turn into oxygen, adding a little more fusion energy and slowly converting the core to a mixture of carbon and oxygen.
At the surface of the star, the end of expansion means that the outer layers stop swelling outward. In fact, the star diffusion actually makes the core swell outward a bit, cooling it off and making the outer layers of the star shrink down a little. On the HR diagram, the star gets a little less luminous and somewhat hotter, putting it into a group of stars called the horizontal branch, or the helium main sequence. These are still considered giant stars. Stars stay on the horizontal branch for about 1% as long as they were on the main sequence. Then they run out of helium in the core and move on to the next phase in their evolution.
What happens next in stellar evolution depends on the mass of the star. So we need to divide up the rest of the story into low mass, high mass, and very high mass stars.
Low mass stars are stars that start out smaller than 8 solar masses, so obviously the Sun is a low mass star. Note that in the late stages of its life, a star usually loses some of its mass. So we usually classify stars by their starting mass, rather than what they have at later stages of their evolution. When the core of a low-mass star runs out of helium, it starts to contract again, just as it did at the end of its main sequence life. This has the same effects that we saw as the star was moving up off the main sequence to become a giant star. As the core heats up, the outer layers of the star swell up and cool off, moving the star up and to the right on the HR diagram.
In the meantime, a shell of helium fusion starts around the core. This is effectively the ash left over from hydrogen shell fusion earlier in the star's life. So now, the structure is a contracting carbon core, a shell of helium fusion just outside of this, another shell of hydrogen fusion beyond that, and then an expanding outer envelope. This structure is shown at the top right, though they've left the outer envelope out of the picture, since it would be thousands of times larger than the core they've shown here. The carbon core of a low-mass star heats up as it contracts, but it can't get hot enough to start fusing carbon. So this marks the end of the line for fusion in low-mass stars.
In the meantime, the outer layers of the star begin to become unstable. The star has become so big that the gravity at the surface is very weak. In addition, instabilities in the 2 layers of shell burning can cause the outer envelope to vibrate up and down. This leads to shells of gas puffing off the star and out into space. During this period, the star loses half or more of its mass to space. Eventually, enough layers of gas escape that the old, hot core of the star is exposed. This core lights up the last few shells of gas around it, producing a glowing cloud called a planetary nebula. Planetary nebulae are some of the prettiest sights in the night sky. They only last for a few thousand years, much less than the billions of years for the star's entire life. Depending on how old the nebula is, and whether the star has a binary companion or not, it can have many possible shapes.
This gas is returned to the interstellar medium, but it's been changed while it was in the star. Some of the hydrogen has been converted to heavier elements like helium, carbon, oxygen, and nitrogen through the nuclear fusion reactions the star went through. So a dying star changes the chemical composition of the interstellar medium. We'll return to this idea several more times as we go through the rest of the course.
The gas a star ejects late in its life, including the planetary nebula, is usually about half or more of the star's total mass. However, that leaves the old core of the star, which is now called a white dwarf. White dwarfs are made mostly of carbon and oxygen, since virtually all of the star's remaining hydrogen and helium has been blown off into space. The core doesn't contract any further because it has become degenerate. This means that the electrons in the core have been squeezed as tightly together as they can possibly get. With between half and 1.4 solar masses squeezed down to about the size of the Earth, a white dwarf has a density of 1,000,000 grams per cubic centimeter. That's 1,000,000 times as dense as water.
White dwarfs are white because their surface is hot. After all, it is the old core of the star that was going through nuclear reactions not that long ago. However, there are no nuclear reactions happening now. Instead, the light we're seeing is caused by the remnant heat inside the star as it slowly cools off. This cooling off process is incredibly slow. There's a huge amount of thermal energy inside the star because of all that mass at very high temperature. However, the heat can't get out very quickly because the star is so small that it has a very small surface area. So it takes hundreds of billions of years for a white dwarf to cool down enough that it no longer produces visible light, much longer than the total age of the universe so far.
Finally, even though white dwarfs are hot, they're still very faint. That small surface area means that you have to be very close to one to see it at all. Even ones a few light years away require a telescope to be seen. This makes them hard to observe, especially when they're near a brighter star that can drown out their light.
Now let's summarize the main steps in the life of a low-mass star. It starts with the gravitational collapse of a cloud of gas to produce a protostar. You can see this on the far left side of the timeline at the bottom. As the protostar continues to contract, its core heats up until it becomes hot enough for hydrogen fusion. Once stable fusion begins, the star enters the main sequence. The main sequence is the longest part of the star's life in which it's generating energy, and the only changes that occur here are very slow and subtle.
When the core has been converted completely to helium, this collapses, causing the outer layers to swell up and turn into a red giant star. Hydrogen shell burning starts during this period. On the HR diagram, you can see the star leaving the main sequence and getting both brighter and cooler. When the core gets hot enough, helium fusion begins and the star enters the helium main sequence. You can see on the HR diagram that the luminosity goes down, but the surface gets warmer.
When all of the helium in the core has been converted to carbon and oxygen, it contracts again, causing the outer layers to swell up one more time and double shell burning to start. This double shell burning is unstable, and the star begins to blow off its outer layers in shells of gas. Some of these are lit up by the old core, forming a planetary nebula.
Finally, all that is left is the old core of the star, now a tiny hot cinder called a white dwarf. The white dwarf will keep cooling for hundreds of billions of years. Here's a question about a pair of stars. They aren't in a binary system, so you can't assume they're the same age, but they are the same mass, just different luminosities. You should explain which of these is older and how you can tell.